Good morning, students. Last session we have discussed about the implementation of DT systems using Z transform. So that Z transform is used to analyze the signals in frequency domain for DT systems. So is h of z is a rational function, numerator polynomial divided by denominator polynomial. Numerator polynomials are called zeros of the system. The denominator polynomials are called poles of the system. So the numerator polynomials, the zeros of the systems are called non-recursive system or FIR system, and the denominator polynomials are called recursive system or IIR filter. So h of z is a mantra of h of z. Sorry. H of z is equal to the summation of k equal to 0 to m bk z power minus k divided by the summation of k equal to 1 to n 1 plus ak into z power minus k. So the numerator polynomials are called zeros of the system. Zeros of the system. The denominator polynomials are called poles of the system. So already we discussed this is also called a FIR system, and this is called IIR system. Okay, this is your implementation of. We'll see implementation of DT systems. Okay, so in this unit we will discuss about the FIR system. Okay, so what is the FIR system? Finite impulse response. Finite impulse response, that is a non-recursive system. Non-recursive system. There is no non-recursive means easy to remember. There is no feedback in the system. So this last class we discussed in detail. No feedback in the system. So it's a finite sequence. The duration, the impulse response is finite impulse. Finite impulse response. Okay. So as I said, the h of z, normally what is the convolution formula? The convolution formula y of n is equal to the summation of k equal to minus infinity to plus infinity h of k into x of n minus k. If you take the z transform, you know that there is a y of n is equal to h of n into x of n minus k. That you can write z transform okay, h of n into z power minus k you can write. Okay, the summation of k equal to minus infinity plus this infinite sequence. Okay, this infinite sequence. So this can be, you can correlate with the FIR equation. So what is the FIR equation? The summation of k equal to, so what is the FIR equation? See what is the FIR equation we written? K equal to 0 to m bk into z minus k. K equal to 0 to m bk into z power minus k. So what is the now? Bk, h of an impulse response is the bk coefficients. Okay, so you can correlate this equation with the general convolution formula, that is a bk into z power minus k, where this h of n which is equal to bn, the coefficients bn, where n is greater than or equal to 0 to less than or equal to m minus 1, 0 otherwise. Okay, this is the FIR equation. So this is a convolution formula, convolution for FIR. Okay, so this h of n, this bk coefficients are equal to the impulse response, where this bn is equal to 0 to, the limits are 0 to here m minus 1. Okay, 0 to m minus 1 window. So this is a equation for the FIR system. Now we will discuss about the general FIR filters. You know the general LTA system. Okay, what is the LTA system? The system linear time invariant system. Okay, linear time invariant system. So in general mantra we know that you can find the output y of n for any input sequence x of n if you know the impulse response h of n. So this system, okay, may be a communication system, okay, communication system, or it may be a biomedical system, or it may be a radar system. Okay, for example, if it is a communication system, this is a system function system. Okay, so for example, communication system, if it is a filter, it may be a filter. You are passing the input signal x of n through the system filter. Okay, so that is a, you can say the input spectrum also. This may be a spectrum wise, frequency domain wise, if you say x of omega. This system modifies its spectrum x of omega according to your frequency response. The frequency response we will discuss in detail now, the h of omega. So this LTA system modifies, if it is a filter, the filter may be classified into FIR filter, or it may be IIR filter. If it is a FIR system, FIR filter, okay, this LTA system modifies the input spectrum x of omega according to the frequency response h of omega to yield an output spectrum which is equal to y of omega. So now you can write, so generally we know that the output is equal to y of omega can be written as x of omega into h of omega, correct? H of omega. Now this x of, now the next the term is band limited signal. The field band, what do you mean by band limited signal? So as a core student, everyone should know this band limited signal of campus. What do you mean by band limited signal? Okay, so consider the signal x of n. Consider the signal x of n, here x of n with the frequency content. Okay, so consider the signal x of n, consider the signal x of n with the frequency content. What is the frequency content? Frequency content with the frequency content in a band of frequency, in a band of frequencies. In analog circuits laboratory class also, for each and every experiment you determine the bandwidth. So what do you mean by bandwidth? It's a band of frequencies. Okay, so you are passing the information, so that bandwidth only contains the frequency content. So what is the frequency range? So in a band of frequency, the frequency content in a band of frequency, so the frequency omega is greater than omega 1, greater than or equal to omega 1, less than or equal to omega 2. So this, now this x of omega is a band limited signal, x of omega is a band limited signal. So if x of omega equal to, for example, if you take a band pass filter, okay, take a band pass filter. So if x of omega is equal to 0 for this is omega 1, this is omega 2, okay, this is frequency response h of omega equal to 0 for omega is greater than or equal to omega 2 and omega is less than or equal to omega 1. So this is example simple. I am explaining the band limited signal for band pass filter. Suppose this signal is passed through this filter, okay, this signal is passed through this filter with the frequency response, So this is not a h of omega, this is a given signal x of omega, okay, this is x of omega. So the input signal is x of omega you are passing. Suppose this x of omega is passed through this filter with the frequency response, h of omega is equal to, you can write c into e power minus j omega alpha. What is the omega range here now in the frequency response? Yeah, greater than or equal to omega 1 and less than or equal to omega 2, 0 otherwise. C into, so the range, this is a band of frequency, okay, where the frequency response is equal to C into e power minus, what is the magnitude here? C, this is C. C into e power minus j omega alpha. The C and alpha plays a role. The C and alpha, okay, the C and alpha are positive constants. So the signal at the output of the filter is, what is the signal at the output of the filter? We know that the signal at the output of the filter y of omega is equal to x of omega into h of omega, is it? So what is h of omega? C into x of omega into e power minus j omega alpha. So what is the frequency range here? This is omega is greater than or equal to omega 1 and less than or equal to omega 2. So this session completely we are discussing the complete fundamental concepts of FIR filter, because the FIR filter is called linear phase FIR filter. FIR filter is called why it is linear phase FIR filter. Okay, so by time shifting property we can write y of the frequency Fourier transform. By time shifting property of Fourier transform we can get the Fourier transform of x of n minus alpha, which is equal to x of omega into e power minus j omega alpha. So now you can write y of omega is equal to c into the Fourier transform of x of n minus alpha. So this y of n is equal to, so now you can write y of n is equal to, you can write this also, c into Fourier transform of x of n minus alpha. So the filter output, so what is the filter output? The filter output is simply a delayed version, a delayed and amplitude scaled. This is a scaling factor, amplitude scaling and the delayed version of the input signal. So the filter output is simply the scaling and the delayed version of the input signal. This h of omega is a complex quantity. The h of omega is a complex quantity. So it's a complex quantity means the magnitude of h of omega and the angle h of omega, which is equal to c into e power minus j omega alpha. The magnitude is a complex quantity, So, the magnitude and phase. Let the phase is theta of omega, which is equal to, this is minus alpha omega, minus alpha omega. The magnitude will be, what is the magnitude? H of omega is equal to C. So, the angle of, now the angle of H of omega is equal to minus alpha omega. We can say that the amplitude is constant and its phase is a linear function of omega, linear function of omega. The phase is linear function of omega. So, the phase is linear function of omega, because the FIR filter, as I said, the FIR filter is a linear phase FIR filter. Wherever the application you require linear phase, you can use because the depending upon the application, you can choose either FIR filter or IIR filter. Okay. So, FIR filter is normally a linear phase FIR filter, and the FIR filter is a more stable filter. Depending on the application, you can choose either FIR or IIR. So, now if any deviation in the frequency response, so the frequency response, if any deviation in the frequency response will, what is the frequency response for all filters? The classification of filters we will discuss now. So, what is the frequency response of, for example, what is the frequency response of that, we can say the desired frequency response of low pass filter, high pass filter. The filter may be low pass or high pass, or it may be a band pass filter, or it may be a band stop filter or band elimination filter. Okay. So, classification will be, what is the ideal or desired frequency response of each filter we will discuss. So, generally in this the frequency response, so if there is any deviation in the frequency response from the ideal results, from the ideal, which results in signal distortion. Okay, signal distortion. When it is called signal will be distorted, the signal will be distorted, the signal distortion. When it will be happen, if there is any deviation in the H of omega, that is the frequency response, that is the ideal frequency response or desired frequency response. So, if any deviation of frequency response from the ideal, which results signal distortion. If it is related to the phase, okay, if the, for example, if phase characteristics is not linear, then it is called phase distortion. Phase distortion. If magnitude is not, okay, if magnitude is not linear, then it is called amplitude distortion. Amplitude distortion. Okay. Distortion. So, what do you mean by filter? So, the filter which passes only the band limited signal. So, the band limited signal for low pass or high pass or band pass band stop filter. So, if there is any distortion in the frequency response H of omega, then the signal will be distorted. If phase is not linear, then phase distortion. If magnitude is not linear, it is the amplitude distortion. And also the ideal frequency response. So, the ideal frequency response or the desired frequency response. The ideal frequency response the ideal frequency response or the desired frequency response is normally periodic with the periodicity of, you can say, 0 to 2 pi, or the range between minus pi to plus pi. So you can map the analog signal omega, the analog frequency omega will map to a digital frequency omega within the range 0 to 2 pi or minus pi to plus pi. Now the ideal characteristics of low pass filter we will see. First we will discuss about the low pass filter. So low pass filter, what is the frequency response of low pass filter? The desired frequency response of low pass filter. So minus omega c plus omega c. So this is minus pi to the range is plus pi. So this is omega. So how you can write the desired frequency response for this one? So hd of omega, which is equal to, this is c, okay, c into e power minus j omega alpha. So whatever this band limited signal here, the range, the omega is greater than or equal to minus omega c and less than or equal to plus omega c, and 0 for the omega is greater than minus pi, this is minus pi, and less than minus omega c. So this one 0 for minus pi to minus omega c and omega c to plus pi, and you can write omega is greater than omega c and less than pi. So this is the, so everyone should know what is the ideal frequency response for all the filters, okay. So this is an example for low pass filter. Similarly, you are supposed to write a high pass, the desired frequency response for high pass filter, a low pass filter, band pass filter, band stop filter. Okay, when you design a FIR filter, you should know the what is the band limited signal for each filters. So we will see another example, not another example, we will see the desired frequency response of high pass filter. So what is a high pass filter? So this is what is a high pass filter frequency response? See, you just remember the frequency response, you can write the equation, okay. So this is a ideal response of high pass filter. So high pass filter, either you can represent 0 to 2 pi or you can represent in terms of minus pi to plus pi. C, this is a constant C, 0. The high pass filter from omega c to pi, from minus omega c to minus pi, okay. So this you should remember. So now how you can write the desired frequency response? Hd of omega, which is equal to c into e power minus j omega alpha, where this omega is greater than or equal to minus pi to less than or equal to minus omega c, this one high pass filter. It is a band limited signal, okay, minus pi to minus omega c, and this omega is greater than or equal to omega c and less than or equal to plus pi, greater than or equal to omega c and less than or equal to pi, okay. Then 0 otherwise. 0 for what? This range minus omega c to plus omega c is 0. So omega between the range minus omega c and less than or equal to plus omega c equal to 0. Okay. This is the frequency response of high pass filter. Okay. Then the frequency response of band pass filter. So what is band pass filter frequency response? I'll write it here. I'll draw the frequency response here. Okay, band pass filter. So just now we discussed about the band pass filter band limited signal. So we'll write the frequency response. So band pass filter, see here band pass filter, this is a omega, see band pass is between the range omega c1 and omega c2. Okay, so this is 0, this is pi plus pi. Similarly here, okay, this is minus omega c2 and plus minus omega c1, this is minus pi. Okay, so this is c. So how you can write the desired frequency response? Here I will write the HD of the desired frequency response will be, okay, c into e power minus j omega alpha, where the omega band pass filter between this range only, omega c2 to minus omega c2 minus omega c1 and plus omega c1 to omega c2 only, this will be c into e power minus j omega alpha. So greater than or equal to minus omega c2 and less than or equal to minus omega c1, and the omega is greater than or equal to omega plus omega c1 and less than or equal to omega c2. This is the band pass filter, this only band pass filter. This is a band pass. So this is a band limited signal. It passes only this frequency and it will reject other frequencies, that is 0. So rejection 0 for which range? Minus pi to minus omega c2 and plus omega c2 to plus pi, and this also minus omega c1 to plus omega c1 also, it will be rejected. So that you have to specify. So omega is greater than or equal to minus pi, okay, and less than or equal to minus omega c2, and omega is greater than or equal to plus omega c1, omega c2, okay, omega c2 and less than or equal to plus pi, and one more, and the range minus omega is greater than or equal to minus omega c1 and less than or equal to plus omega c1. So this is a band limiter signal, which only this band limiter signal which passes only the band limiter signal and rejects the other frequencies. That is a desired frequency response of band pass filter. Okay dear. Similarly, you can write the frequency response of band pass band stop filter. Band stop filter, because everyone should, the question may be either you have to design a filter for low pass or band high pass or band stop filter. Similarly, so the frequency, first I will draw the frequency response curve HD of omega. Okay, so this is a band stop filter. Now this is a band stop filter. So this minus omega c1 to I think the first we have discussed minus omega c1 to plus omega c2. Okay, then it will reject the other frequencies. For example, minus omega c2 This is minus omega C2 to minus pi, okay, plus omega C2 to is opposite to band pass filter. Omega, this is omega C1, okay, this is omega C1 minus omega C1 plus omega C1 plus omega C2 and plus pi omega. So how you can write for this band stop filter? So the HD of omega, which is equal to C into e power, this is C, okay. So actually it should be equal, okay, not this one. So C is a dotted line, C e power minus j omega alpha, where the, how you can define the omega now, greater than or equal to minus pi, okay, less than or equal to minus omega C2, then band stop filter, only this will be rejected, and omega is equal to greater than or equal to minus omega C1 minus omega C1 and less than or equal to plus omega C1, and one more, and W is greater than or equal to omega C2, that is a minus omega C2 and less than or equal to pi, okay. So 0 for which case? So omega is greater than or equal to minus omega C2 to minus omega C1 and plus omega C1 to plus omega C2. So you can write that is a minus omega C2 and less than or equal to minus omega C1, and this omega is greater than or equal to omega C1 and less than or equal to omega C2. So it's a band stop filter ideal response characteristics, okay. So before designing the FIR filter, everyone should know. So in this session, what do you mean by band limited signal? What is the role of filter? The system, the LTE system may be a communication system, for example filter, which is used to cancel the noise, or which is used to cancel the interference. So if any signal passes through the filter, any spectrum x of omega passes through the filter, the output response, which yields the output response, okay. So the desired frequency response, so which gives the output spectrum y of omega, where the signal may be distorted. If there is any change in the frequency response characteristics, the output will be distorted, that is the signal will be distorted. So if there is any deviation in the amplitude, then it is amplitude distortion. If there is any deviation in the phase, then it is a phase distortion. So we have seen the desired frequency response of low pass filter, high pass filter, band pass filter, band stop filter, okay. So the next session we will discuss about the how to design a FIR filter, okay. By using window method we will see, okay. Thank you.